Okay, so now we are going to talk about modeling. And we will use all the concepts that we have learned in the previous few chapters in modeling. And I am going to give start with the regression models, which are the simplest model that one can have, fitting just a straight line. And then we go on to more complex models. The advantage of these simple models is that they teach you the techniques that we want to teach you. So what is a good model? How do you estimate the model parameter? How do you allocate the variation? How do you find the errors, confidence intervals, and the test about the assumptions? So first of all, a regression model is one that predicts a response for a given set of predictor variables. So what is a predictor variable? What is a response variable? So you have something that you want to predict. That is the response variable. That is what we call response variable. But you want to predict based upon several other variables, such as room temperature or workload type or the number of users. Those X parameters, X variables actually, those are called predictor variables. So the response variable is the Y variable, and the predictor variable are the X variables. These are the things that you change. Those are the factors. The X are the factors, and the Y's are the outputs. Now, if you keep the relationship linear, then it is called linear regression. The relationship could be non-linear, where, for example, y equal to x square. And we will discuss that too, but for the beginning, we will start with a very simple linear model. Y is equal to a times x plus b, something like that. Or y equal to a1 x1 plus a2 x2 plus b, or a0, something like that. And if it is just one variable predictor, one x variable, then it is called simple linear regression model, SLR. And so we will start with the simplest of all, and that is simple linear regression. Just one predictor, one response, and linear relationship. And we will see how much math there is just to do that correctly. So, suppose these red dots are the measured observations, and you say, well, rather than giving the measured observations, I will give you a straight line. So a straight line is your model. All right, you're not going to, because these red dots could be a million of them, right? So you don't want to give them a million numbers, you just want to give them a straight line. You will say, well, the performance is 2 times x plus 3. That's much easier than giving all these million numbers. So that's a model. That looks like a good model in this case. Looks like a good model in this case, but doesn't look like a good model in this case. Does it? Because yeah, right. So the thing is, in this case, the line does not really represent the points. This line does not represent the point. It could be a different line that you need. So what is wrong with this line? Basically, so that's the next step, is that there is what the model says and what the real world says is different. So here, the real world says this red dot, and if you draw a vertical line, that is what the model says. Right? So that's the error, modeling error. Right? And so there is modeling error at every point. Here, those modeling errors in the last one, those modeling errors could be large. Some of them are very large. That's why it is not a good model. Right? And let's assume, and this is common, this is one of the assumptions, is that in your system that you have, modeling errors, whether it is on this side or that side, are equally damaging. So basically, whether you over predict or under predict, equally damaging. Now you could have a case where this is not the case. You will have to find a different model. But for now, if we assume that the plus and minus errors are equally damaging, then all you do is you take the square of the errors and you minimize that. And another thing a good model would do is that it would be so that the first of all the errors, overall errors would be 0, in the sense that whatever your model says over million observations and whatever the million observations are, on the average they are the same thing. So the average of both of them are same. So the average error would be 0. The standard deviation will be minimum, and that's why you're taking the square and minimizing it. Okay? By the way, we will use the word residual for the same thing, for the errors. We will use the word error or modeling error for the same thing. Okay? Okay. So now our model is y hat equal to b0 plus b1x. It's a linear model. It has two parameters, a slope and intercept, and we put a hat here because this is our best guess. This is our best prediction. Okay? And actually, also this represents our prediction. This is a model as opposed to y, which is measured. So the measured is different from the predicted, and there is an error. EI equal to yi minus yi hat. So our requirement is that the sum of the errors should be 0. So we should estimate b0 and b1 such that this quantity is 0. You get one linear expression, one linear equation in b0 and b1. And second thing you want to do is that the square of the errors is minimum. So you want to minimize that. All right. Now minimizing this, you know how to minimize anything, right? But for minimizing, all you do is differentiate by whatever you want to minimize with and set it to 0. So if you differentiate this thing with b0 and set that to 0, and differentiate with b1 and set that to 0, you get those equations to get b0 and b1. So we did that and we came up with b1 is sigma xy minus nx bar y bar divided by sigma x squared minus nx bar squared, and b0 is simply this. Alright, x bar is the mean of x, y bar is the mean of y. Sigma xy is simply sum of xi yi, sigma x squared is sum of x squared, and so on, the common meanings. So we can take an example. The number of disk IOs and the processor times of 7 programs were measured as 14, 2, 16, 5, and so on and so forth. So this is the disk IO and this is the processor time. And somebody believes that they are very much related, and therefore you should be able to predict one from the other. So n equal to 7, sigma xy you can calculate, sigma x you can calculate, sigma x squared you can calculate, and sigma y squared, x bar, y bar, etc. etc. Put all those numbers in the formula, and you get b1 equal to 0.2438 and b0 is equal to minus 0083. And therefore the model is CPU time, which is the second number, is equal to minus 0.083 plus 0.2438 times the first number of disk IOs. Alright, this much you would have done in high schools or something whenever you fit the line. So I'm going to move on and show you some new stuff. And this is how the line looks like. You plot the graph. Looks pretty good. X versus Y. The errors computation, basically you calculate yi hat from the model that you fit. This is yi hat, this is yi, take the difference, that is the ei, error, and you should add the errors, so this should add up to 0. If they don't add up to 0, then obviously there is some mistake in calculation. So errors should add up to 0, then you take the squares of the errors and add them up, you get this value, and so this value is called sum of squared errors, right? Sum of squared errors. Now we will introduce that term in a minute, but the next few slides go into the derivation of this formula, B1 and B0. Actually, it's very straightforward. I will briefly explain to you how do you get there, and it's not really necessary to do in very much detail. But we know that the y hat is B0 plus B1x, so the errors basically is yi minus this quantity, and this would add up to 0, and therefore this would add up to 0. Y bar minus B0 minus B1 x bar, this is one equation we get, equal to 0. And that gives you B0 as y bar minus B1 x bar. Now how do you get B1? Well, you substitute B0 in this right here, and so you get EI equal to this quantity, because you have substituted B0 there. So yi minus y bar minus B1 times xi minus x bar. Now you square it, and then you differentiate with B1. When you square it, you get this expression where something is squared plus 2B1 times some quantity plus B1 is squared. So you differentiate that with respect to B1. Now this quantity, So all I've done is from here to there is this divide by n minus 1. So if I divide by n minus 1, that allows me to write these things in a simple way. So this whole thing is sy squared. This whole thing is sx squared, and this thing is the covariance s square xy. So now I can differentiate it much easier. Now this is a simple term. So we differentiate that, and we get that B1 is simply s square xy divided by s square x, and so we can write down the expressions. So let's take this is a homework again. Let's see what we will do is this homework I think I want you to do, but this will be due Monday after next. You don't have to worry about this week, but I do want you to come up to speed by the time you come back after the exam. So 25th. Is it 25th? Yeah, 11 plus 14, 11 plus 8, yeah. Yeah, 25th. This will be due on 25th, Monday. It looks like too far away.
It would be 11 days from practice.
Yes, today is 13, so 24th, yeah, whatever. Yeah. So anyway, so this is an exercise which simply says that you have time to encrypt a k byte record. So if the record size is 128, you have these 3 observations. If it is 256, there are 3 observations. So total you have 1, 2, 3, 4, 5, 6, 7, 8, 24 observations. All right. Values of x can repeat. Values of x can repeat. So basically, these are 24 observations. Okay. And so given those 24 observations, you have to fit the linear regression model, which simply means that you have to find out B0 and B1 by putting into those formulas. Now we are going to do something slightly new, which you may not have done before, but that is that we know the errors. So the variance of the errors, if you didn't have any regression, then you would have said, well, this is y, and you will have just given one number, which is y bar, and that would be your error without the regression, y minus y bar. And so that would add up to the variance. Actually, if you just sum of the squares of the errors and divide by n minus 1, you get the variance of y. Right? But now that you have introduced x, So you're not just taking y values, but you are taking that it is related to x. So now what you have gotten has to be less than what you had before. And let's see how that can be divided. So right now, this thing, y minus y bar whole square, can be written into two parts. Y squared minus n times y bar square. And so this is called sum of squares of y. SSY. This is called SST, sum of squares total. Sum of squares total, which consists of two parts, sum of squares y and sum of squares 0. So this y bar is actually, we are using SS0. It will become clear as to why we call it 0. But anyway, basically, SST can be divided into two parts. One part is SSY and another part is 0. And the difference, now the thing is that with the regression, what you have done is you have reduced the errors. You have reduced the errors from SST to something less, and that difference is called sum of squares due to regression, or explained by regression. So SSR is simply the difference that you have reduced. So you started from here without x. This is what you had, but with x you have sum of squared errors, SSE. So the difference between these two is called SSR, or SST can be written as SSR plus SSE, or you can take the fraction, you can divide the whole thing by SST, and you can say, well, basically, if you divide the whole thing by SST, then you get SSR upon SST is equal to SST minus SSE upon SST. Okay? And that R square is what is normally you have already heard before. It's called coefficient of determination. That is the ratio of what fraction of the variation is explained by the regression, and so that is a ratio, right? It turns out that if you were to do the correlation Rxy, that would be S square xy divided by Sx xy. It is not the same thing as it is related to the coefficient of it is related to the coefficient of determination. So if the correlation coefficient is 0.9, the coefficient of determination is the square of 0.9. Anyway, let me give you an example that will make it clearer as to what we are talking about here. Okay. So for the previous example, that disk IO CPU example, if we calculate the SSE, that can be calculated two ways. The simplest way is that table that we made before, and in the bottom of the table there was 5.8187, if you remember the right column. So that is sum of square errors. But you can also get it by this formula, which is y squared minus b0 by minus b1 xy. So you can calculate y squared, calculate y, sum of y's, calculate sum of xy, and put it together. Anyway, you get 5.87. You can calculate SST as the total variation, and so you calculate the sum of square y and then minus n times y bar square, and you get 2.20571. So the point to notice is that if you didn't know x at all, then the best you could do is give the mean, and then your errors would add up to 205.71. Now that you have x, your errors add up to only 5.87. All right. What that means is that you have explained 97% of these errors squared. Between 5 and 200, you have explained 97%. Everybody sees that? And so that is what this R square is all about. This coefficient of determination simply says what percentage of variation you have explained. Now, from now on, I will use a new term called variation. It's different from the variance. Variance is a statistical term which is written in the probability books and is calculated by the formula that we learned, which was 1 upon n minus 1 times some whatever it is, right? Standard deviation and variance. Whenever we say variance and standard deviation, we mean those things. When we say variation, we are much looser. Variation we just simply actually is basically we mean by this sum of squares. This sum of square is not variance, right? But it is somewhat related to variance, right? And so this is what we call variation. And so what we are saying here is that X explains, or this regression explains 97% of the variation. Okay, that means sum of the squared errors. It explains 97% of the sum of the squared errors. Without the regression, sum of squared errors was 199. With the regression, it is only 5. All right, let's see. So now, first thing now we notice is we now know R squared and what it means, which you probably knew before, but now we have the term variation. And if you really wanted to get the variance of the errors, you will have to divide the SSE by n minus 2. That would be the variance of the error. And the standard deviation will be square root of that. Why n minus 2? Because the errors have n minus 2 degrees of freedom. Why n minus 2 degrees of freedom? Because when you are given a sample of n observations, you already calculated 2 parameters, B0 and B1, before you got to the errors. If I gave you n minus 2 of those errors, you can easily calculate the last 2. Okay? And so, the degree of freedom that errors have is only n minus 2. And therefore, the standard deviation is SSE divided by n minus 2. So it's a square root of that. So this is called mean squared error. This variance part is called mean squared errors. Mean squared errors. Squared error, sum of squared errors divided by the degrees of freedom. That is mean squared error. When you take a square root of that, that is standard deviation of errors. SSY has n degrees of freedom because it is obtained from n observations. If I gave you n minus 1 observations, you couldn't get the next one. So that is full n degrees of freedom. SS0 has only 1 degree of freedom, which can be because it can be computed just from by var. And SST has n minus 1 degrees of freedom because only by var must be calculated before you can get SST. You cannot get SST without by bar, right? Yeah, go ahead.
Is there any relation between any correspondence between the variance of errors to the variance of measurements? I mean, if the variance of measurements is really, I don't know, high, it means that my regression formula will be such a...
No, hold on. So two things. You could have a very high variance of the measurement. But if you have a very good model, it will accurately predict everything. Okay? If you have a very good model, then you could get errors to 0.
Although I have a really large variance.
In the beginning you had large variance, but if you had a good model, so let's say let's say we are predicting the height of the mountains based upon their location. All right? The height of the mountains could vary from this little to that big. So there is large variance. But somehow somebody gave me the location, then I have a formula which gives me exactly the same value at every mountain. So the errors are 0. Right? So there are two errors you are confusing. Measurement errors and the modeling errors. Measurement errors are those when I went to measure the mountain, height of the mountain, I could be off by 1 meter. That is measurement error. That I can't help it. Right? Modeling error is after I modeled it, what is the difference between the model value and the measured value. That should be 0 in the ideal case. And the original variation has nothing to do with original variation. Could be just a natural phenomena that things are different. Alright, so original variation could be very large, but the model should be so good that it can take care of any of those things, right? So that is a good question. Basically, so we understand that these are the modeling errors we are talking about, and what I wanted to explain the degrees of freedom. So for every quantity that we have done so far, there are degrees of freedom, and the easiest thing is to remember by this formula. SST has n minus 1 degrees of freedom, because to calculate SST you need byvar. SSY has full n degrees of freedom, because you don't need anything to calculate SSY except the n values. SS0 has 1 degree of freedom, and SSR has 1 degree of freedom, and SSE has n minus 2 degrees of freedom. Okay, it turns out just like these squares add up, the degrees of freedom also add up. The degrees of freedom also add up, and so now when you do the standard deviation of the errors, you don't divide by n minus 1, you divide by n minus 2. There will be other quantities that we will see later on where you divide by n minus 3, and so on. Okay? Alright, so now let's put the degrees of freedom. So for the disk IO CPU data that we had, SST was 205, and SSY, so that was calculated from SSY and SS0, 205. That was divided into two parts, SSR and SSE. SSE is 5, SSR is the whatever is left over from between the two. And then degrees of freedom are 6, 1, and 5. So the mean squared errors is SSE upon n minus 2, which is this 5.87 divided by 5. So mean squared error is 1.17. Standard deviation of error is square root of that is 1.08. The regression intervals, now interesting thing is that we calculated B0 and B1, but B0 and B1 are in English letters, estimate of something that we don't know. Beta 1, beta 0 and beta 1, those are the Greek letters for the population values. If you would have had whole world measured, then you would get the population model, right? So those are random numbers themselves, and therefore we need everything. We need their mean, we need their standard deviation, we need the confidence interval for B's as well. So B0 has a standard deviation which is given by this formula. B1 has a standard deviation which is given by this formula, and these are actually possible to derive if you just know that the B0 is whatever the formula for B0 is, and we assume that y is normally distributed, and therefore the sum of squared is normal. Sum of square is actually has chi-square and all that. I would not go into that detail, but basically for now you should just know these formulas. Okay, so the standard deviation of B0 is this, standard deviation of B1 is that. Now we need to know the degrees of freedom. The degrees of freedom of both B0 and B1 are basically equal to the errors, so they have the n minus 2 degrees of freedom. And now you can use the confidence interval by doing B0 minus plus T times SB0 and B1 minus plus T times SB1. If the confidence interval includes 0, then that parameter cannot be considered different from 0. Okay, so again example will help, so I'm going to go take the example. So for this disk IO CPU data, SB0, if we put all the numbers in the place, will come out to be 0.8311, and SB1 will come out to be 0.0187, and the value mean we already had before. We'll see them in the next slide. So the degree of freedom is 5. We had n equal to 7, n minus 2. The errors have the degrees of freedom of 5. And so we use that 5 degrees of freedom. And for 90% confidence interval, we read the t values at what value? T at 95, 97. Give me a number. We need 90% confidence interval, two-sided. Yeah, so we need 95. So you go to the table, read 0.95 at, since this is a t value, we need to have degrees of freedom. So 5 degrees of freedom. So you go to the fifth row and read 0.95, you will find 2.015. And then you put down this standard deviation and you get this value for B0. Similarly, you do for B1 and you get this value for B1. Now, interesting thing is that this value, the intercept, can be anywhere from 0.16 to 1.6. Minus 1.6 to plus 1.6. So the intercept could be 0. All right, but this is clearly not 0. This one doesn't include that. So now you see, like this value looks, the value of B0 before 0.8 looked like a big value, but when you did the confidence interval, it turns out that that's really not significant. All right, so here is a case study. And case study means these are real numbers from real study. So we did a study of Unix versus Argus. Everybody knows what is Unix. That's an operating system. Argus was another operating system being developed at MIT during the time when I taught this course. So basically the students did the work. Unix versus Argus. And so for different data bytes, they did remote procedure call. That means they sent procedure from one machine to the next and executed there. If the data was 64 byte, it took 26.4 seconds. And obviously these are not paired observations because these values are different, right? And when they said 92 on this machine, it took 32.8 and so on. So these people decided to do 2 regressions. The first regression is for Unix and the second one is for Argus. Now we could all question the validity of the model here, but I will show you that in more detail as to how to test the validity later on. But for now, let's just work with these 2 linear models. So time on Unix is this and time on Argus is that. The regression explains 81% in case of Unix and 75% in case of Argus, and you can see why. In case of Argus, the errors are large. So the model is not that good. So now the question is about per byte quantity. Here it takes 0.03 per byte, it takes 0.034 per byte. Are these different? Right? We are not really interested in anything else. We are interested right now in per byte thing, right? And so to answer that question, we need to do the confidence intervals on those 2. So the confidence intervals, we calculate B0. For the Unix case, we calculate the mean value and the standard deviation of B0. So we use that formula to calculate the standard deviation of the errors first, and then from that standard deviation of B0, and then we get the confidence interval using t values, and then B1 we get the confidence values, and for B0 we do the same thing, and B1 we do the same thing. Now we look at these 2 confidence intervals. Do they overlap? Do they overlap? That's the question. So the highest of this is 0.04 and the lowest of this is 0.01. Highest of this is 0.02 and the lowest of this is 0.02. Okay, so they don't overlap.
Hold on a second. So there, the B1 parameter for units is 0.017, but on the previous side, I thought it said 0.030.
So one of them is wrong. Which one is it? What does it say in the book? Anyway, so I mean we'll figure that out and put the right value here, but the idea is clear, right? Is that you just compare the quantities, and both of these quantities are random numbers, and both of them have confidence intervals, and whenever you want to compare two random quantities, you compare the confidence intervals and see if they overlap. If they don't overlap, you can make a decision right then and there. If they overlap, then what? No, then you have to see whether the mean of one is in the interval of the other. Then you can make a decision right then and there. Right? If, and by the way, this you should be ready for the exam. You should just have this in your brain. So I may give you some numbers and say, do they overlap or not? So I mean, you have to figure that out. And if they overlap so little, that means you cannot make a decision. The answer would be, don't know. Need more analysis. Right? So in this case, there is no overlap, as written here. Although one of the numbers is wrong, we know that. Did you figure out? Yeah, we will figure it out next time.
It's the same in the book, so we may need to actually work through that.
Yeah, okay. I need to work through it, yeah. So this is homework 14B, which basically you are going to continue your previous homework 14A and compute the confidence intervals. All right, I think that would be a good point to stop, and then we will go into the predictions next time.